The limits of my language mean the limits of my world. You know, this profound thought by philosopher Ludwig Wittgenstein actually perfectly frames one of the most monumental challenges in science. For decades, giving machines the ability to understand our language, to perceive our world, and to process information the way we do, well, it seemed like an absolutely insurmountable limit. But as we're seeing today, machines are breaking through those limits, and they're doing it by borrowing a design directly from nature. So, welcome to this explainer. Today, we are going to unbox the digital brain and really explain neural networks. You know, the actual engines driving today's massive AI boom. We're going to demystify the magic behind the technology. So don't worry, there's no dense coding jargon here. Just a really clear, fascinating look at how these systems actually work under the hood. Here is our quick roadmap for today. First, we'll meet the digital brain, then look at the anatomy of a neuron. Third, we'll cover how the machine learns, move on to the evolution of deep learning, and finally, look at different networks for different jobs. All right, let's dive right into section 1, meet the digital brain. To really understand AI, we have to look at the biological neuron, because it's the direct inspiration for the digital mind. Think about your own brain for a second. You have roughly 86 billion of these neurons firing away, and incredibly, they run on just about 20 watts of power. Way back in 1943, a neurophysiologist named Warren McCulloch and a logician named Walter Pitts looked at this biological marvel and proposed a simplified mathematical model. They just wanted to show how simple brain-inspired units could compute logical functions. The crazy thing is, they weren't even trying to build a modern computer. They were just laying the conceptual groundwork. So, how does that translate to a machine? Let's draw a direct comparison. On the biological side, you have dendrites that sum up electrochemical signals. In the artificial world, that translates beautifully to a weighted sum of numeric inputs. Biologically, a neuron has an all-or-nothing firing threshold, right? It either spikes or it doesn't. Artificially, we use what's called an activation function to mimic that exact threshold. And what about learning? Well, in our brains, it's synaptic plasticity. In a machine, it's a mathematical process called gradient descent. It's just this brilliant direct translation from biology straight into math. Which brings us to section 2, anatomy of a neuron. Let's open up the black box and look at the multi-layer perceptron, or MLP. Think of it as a feed-forward network stacked in layers. There's a great analogy from our sources that uses a basic spam filter. Imagine raw text inputs, the actual words from an email, entering the bottom layer of the network. Those signals flow forward through the hidden layers in the middle. Those hidden layers extract higher-level context. And eventually, the signal reaches the top output layer, which hands us a final probability. Basically, it asks, is this email spam or not? Now, the crucial part is how it actually computes that answer. The underlying math relies on two main parameters, and it helps to just visualize them as physical dials and knobs. Weights act exactly like dials. They control how strongly a specific input influences the decision. So if the network sees the word prize, it might have a really high weight, cranking the dial all the way up for a spam prediction. Biases, on the other hand, act as threshold shifters. They are built-in values that artificially shift a neuron's activation threshold, which basically allows it to fire even if the raw inputs coming in are relatively weak. Okay, let's move to section 3, how the machine learns. Now that we know what the network looks like, how do those dials adjust themselves? IBM outlines this training loop in 4 distinct steps. First up is the forward pass. Inputs flow through the network so it can make a prediction. Second is error calculation. The network compares its prediction to the true correct label and measures its error using what's called a loss function. Third is the backward pass. That error gets propagated backwards through the network. And finally, step 4, the weight update. The network adjusts its weights and biases slightly in the direction that actually reduces the error. And it just repeats this thousands or even millions of times. I absolutely love this metaphor from our sources to anchor this complex concept. Imagine the forward pass as turning on the water through a massive network of interconnected pipes, and you're just checking to see if it comes out the right faucet. The error calculation tells you if it didn't. Then comes the backward pass. Imagine turning the water off, and a tiny army of squirrels suddenly races backwards along all those pipes. These squirrels are frantically tightening and loosening the valves, which represent our weights, to get the flow exactly right for the next time you turn the water on. But of course, behind those playful squirrels is some really serious, elegant math. In digital neural networks, the role of those squirrels is played by a brilliant algorithm called backpropagation. Backpropagation uses the chain rule from calculus, along with optimization methods like gradient descent, to estimate exactly how much to change each and every single parameter. It literally walks backward, mathematically, ensuring the network minimizes its error over time. Let's zoom out a bit for Section 4, the evolution of deep learning. Tracing this historical timeline is just incredible. I mean, it starts way back in 1943 with that McCulloch-Pitts model. Then in 1958, Frank Rosenblatt introduces the perceptron for simple pattern recognition. By the 1990s, we were seeing statistical language models relying on Markov assumptions. But the real explosion, that happened in the 2010s. The deep learning boom was suddenly powered by vastly more data and practically unlimited cloud computing power. That let us stack many, many layers, hence the term deep learning. And that paved the exact path to the 2020s and the rise of the massive large language models we see today. And that brings us to our final section, Section 5, different networks, different jobs. It's important to know that not all neural networks do the same thing. Take the convolutional neural network, or CNN. CNNs are the undisputed kings of computer vision. They're specifically designed for grid-like data, like the pixels in an image. Instead of every single neuron connecting to every other neuron, they use local convolutions and filters. This lets them detect spatial hierarchies. So they first find simple edges, then they combine those into shapes, and eventually they recognize complex features like faces or objects. Now, for sequential data like text or time series, we traditionally used recurrent neural networks, or RNNs. RNNs use looping connections, which gives the network an internal memory across time steps. But they have a major flaw. They suffer from the vanishing gradient problem. It's kind of like a long game of telephone, where the influence of those early words just completely fades away over long distances. To solve that game of telephone, researchers created an absolute breakthrough architecture called transformers. Transformers largely replaced RNNs for natural language processing. Because instead of processing everything sequentially, word by word, they use something called attention mechanisms. This allows the network to look at an entire, long sequence of text all at once and mathematically calculate which words should attend or relate to other words regardless of how far apart they are in the sentence. This is the exact architecture that paves the way for tools like ChatGPT. But here is where things get really fascinating. Once we had that transformer architecture, researchers discovered the scaling law. By simply scaling up the model size and the training data, performance just skyrocketed. I mean, we went from relatively small models to GPT-3 with 175 billion parameters, and then Google's Palm with 540 billion parameters. And crossing these massive size thresholds unlocked what we call emergent abilities. These huge models suddenly showcased complex problem-solving skills, like in-context learning, that simply did not exist in their smaller predecessors. They were figuring out features directly from the massive data without being explicitly programmed to do so. Which leaves us with a truly profound thought to end on today. We have evolved from a simplified 1943 mathematical concept mimicking our 20-watt brains all the way to colossal digital networks capable of emergent, almost magical abilities. So, if merely scaling up gave us these entirely new, unprogrammed capabilities, what exactly emerges when we scale up next? Keep that question in mind as the digital brain continues to evolve. Thank you so much for joining me on this explainer, and as always, keep learning.